How's it going, everybody, and welcome back to another 1001 MSc online tutorial video. My name is Brock Grant, and today we're going to be going through some questions regarding the properties of liquids and solids. So, there's some prerequisites for this module. Again, I highly recommend you check out the first video of this module, and also look at stoichiometry and be able to convert units. This module is particularly math hungry, so make sure that you are comfortable with converting units and rearranging formulas before you attempt this module. Because if you aren't too sure, it will be a bit confusing, so I recommend recapping on that first. So we're going to be using some questions from two different modules today. So we've got chapter 13 and chapter 14. So let's hook into it. So let's begin now on page 314, question 24. So the question says, how many joules of energy must be removed from 325 grams of water at 35 degrees in order to form ice at 0 degrees? So the question is saying how many joules of energy. So it wants to know how much heat or energy is being removed. So what we do is, the key pieces of information from here is that we have 325 grams of water at 35 degrees, and we want to see how much energy we have to withdraw to turn it into ice at 0 degrees. So this requires two different things. Our first step is determine the amount of heat lost to cool it from 35 degrees to 0 degrees. Now, we do this by using our specific heat formula. So, Q is equal to mc delta T. So we have a look here. So Q, we don't know, because that's what we want to find out. We want to know how much heat is being moved, is equal to the mass. So the mass is 325 grams times the specific heat, which is 4.184 joules per gram degrees Celsius, multiplied by the change in temperature. So the change in temperature is going from 35 degrees to 0 degrees. So we're going to do 0 minus 35 degrees Celsius. And what happens is when we put this into the calculator, so you'll notice that I've put these all in individual brackets. It's always good habit to do that so you don't make little math errors. So by multiplying all of these together, we get a total heat lost of negative 47,593 joules. However, that is not the final answer, because we also need to take into account the fact that it went from water to ice. Now, remembering that when we're going from ice to water or water to ice, this is the heat of fusion, and the heat of fusion is equal to 335 joules per gram. So we have 325 grams of water. So we have 335 joules per gram multiplied by 325 grams will equal to the heat of fusion. Therefore, the amount of heat responsible for the heat of fusion is equal to 108,875 joules. Now, we need to add these two values together in order to get an accurate number. We have negative 47,593 plus negative 108,875, and that gives us a grand total of 1.57 times 10 to the 5 joules of energy. Okay, let's move on now to question 30. If 9,560 joules of energy was absorbed by 500 grams of ice at 0 degrees, what would the final temperature be? So, here is where we need to again use our specific heat formula. So Q is equal to mc delta T. So we have our amount of energy, so that's 9,560 joules, is equal to the mass, 500 grams, times the specific heat, times the final temperature. So we know the final temperature is an unknown. So we go X and we subtract the initial temperature because we want the difference. So it's going to be minus 0 degrees Celsius. So we can rearrange this. So by moving the 500 over, so it's the mathematical operation here is a multiply. So that's going to turn into a divide. And the same can be said for 4.184, so our specific heat. So by moving both of these over, we're going to get 9,560 joules divided by 500 grams times 4.184 joules per grams degrees Celsius is equal to X, because X minus 0 is still X. So 500 times 4.184, and that answer is what we use to divide 9,560. That means that X is going to equal to 4.61 degrees Celsius. So let's look here. So if we have 75 grams of ice at 0 degrees, and we add this to 1.5 liters of water at 75 degrees. So if we have our little cube of ice, and we plonk that into our beaker full of water at 75 degrees, what would the final temperature be? Now, with all questions like this, unless stated otherwise, we assume that there is a nice sort of lid on the top and that no heat is lost to its surroundings. So we're assuming that it's not, cooling down or heating up due to the external environment. We're assuming it's all insulated inside. So the first thing that we need to do is we need to look at this question and go, okay, what is the final, what do they want? So they want the final temperature. Now, a big thing we need to acknowledge here is we have two different objects. We have ice and we have liquid. So we sit here and go, well, okay, do we need to calculate what the final temperature of the ice and what the liquid water would be? And the answer is we sort of do, but we don't, because both of those temperatures will be the exact same. Because what will happen is the colder item, which is ice, will get hotter, and the hotter item, which is the beaker of water, will get colder until they reach an equilibrium, until they're the same. So this is how we can tie these two parts together, because we know that the final temperature of both the ice and the beaker of water will be the exact same. Here we've got our question, here's where we've got our first point here, and again we realize that the final temperature for both of these will be the exact same. Here, what I do is I'm going to combine these two this formula together, because we know that the amount of heat that is gained by ice is going to be the exact same as the amount of heat lost by the beaker of the hot water. So because of that, we can make these two, we can fuse them into one. So we can write the equation as mc delta T, because remember, Q is equal to mc delta T. So how we've written that the heat of the heat gained by the ice is the same as the heat lost by the beaker, we can say the same thing as the mc delta T of the ice is equal to the mc delta T of the hot water. So essentially what I've written here, so this and this mean the exact same thing. And that's what I have done down here. Now, here's where things get a little bit more tricky. So I'm going to just draw a quick temperature scale. So we have our ice, which is at 0 degrees Celsius. And we have our heat of the hot water, which is 75 degrees Celsius. And somewhere around here, in between these two values, we don't know where, is our final temperature, which we will denote as X. So what we can do is we can look at this gap here. So we can go 75 degrees Celsius minus X. And what that will do is by having this formula like this, so it's the final temperature and the initial temperature, this will give us this gap here. But with the ice, I can write this part, so this gap over here, as X minus 0 degrees Celsius. Now, I can hear you guys already going, well, hang on a second. How the hell did you do that? How did you know that? Why have you got the X's on different sides? What's going on? The biggest thing here to note is we know already that the temperature of the hot water in that beaker is going to go down. It's inevitable, okay? If we add ice to hot water, it's not going to get hotter. It's going to get colder. So what I've done is I've said, yes, we don't know what this unknown is, but I know that this 75 degrees is going to get colder. It's going to go down. So I did 75 degrees Celsius minus X. Now, the opposite can be said for the cube of ice. We know that cube of ice is going to get hotter, okay? Because it's going into a hotter environment. So this is where I can swap the X's around because I know that this temperature is going to go up, whereas this temperature is going to go down. So if we combine the two algebraically like this, we can see that we have 75 degrees minus X. That will give us this gap. And X minus 0 degrees gives us this gap. That means we can then determine where X actually is. So now what we can do is we can look at our formula that we'd written out here and we can start to insert the values. So the mass of the hot water we know is 1500 grams because remember the density of water is 1. We know the specific heat of water. We know that it takes 4.184 joules of energy to heat 1 gram up by 1 degree Celsius. Now the tricky part here is 75 degrees minus X, and that's what we did up here. So we've got our difference in temperature. Now, our next part here, again, we need to remember that this is going from ice to water or liquid. So we need to include the heat of fusion because we need to account for a changing phase. So this is where we've got our heat of fusion to account for the change in phase. So we have the mass of our ice cube. We then have the specific heat of our ice. And again, we have our change in temperature, which we got from over here. Now, our next step that we need to do is we need to solve for X, okay? We know that X is going to be the same with both of our, on both of our sides, so here and here. Okay, so they're going to be the same, so now we need to rearrange and solve. Be careful here, okay? This is where it is so easy to make a simple mistake. Our first step that we need to do is we need to expand the brackets. So we have 6,276. So we got that by 1,500 times 4.184. And we multiply this by 75. And we also need to multiply this by negative X. Okay? It's the same here with the 25,125 joules. So that was done by multiplying these. And then we have our 313.8. So we need to times that by x. And then we need to times that by negative 0, because we've got this little, the subtraction sign there. Now that gives us, so 6,276 times 75 is 4.27 times 10 to the 5. Then 6,276 times negative x gives us negative 6276x is equal to, we've got our energy here, that's fine. So then we have 313.8 times x, and that gives us 313.8x. Then we've got 313.8 multiplied by negative 0, and anything multiplied by 0 is 0. So I haven't placed that in here. Now that we've done that, we can now start to rearrange some of these values to simplify. So what we can do is we can start to shuffle these things around so that we have all the x's, so our unknowns, on the same side. So by moving this negative 6276x over here, this turns into a positive value, and that's why we can see this is now a positive. And our 25,000 joules, as this moves over here, because that was a positive value, that now turns into a negative. So you can start to see now, especially under time pressure, it can be very easy to muddle these things up, to not expand the brackets properly, to forget to change the plus to a minus. So these sorts of questions require a lot of attention. So we now simplify. So we've got 4.27 times 10 to the 5 minus 25,000. And that will give us 445575 joules. And we have our x. So we can add these together because they have the same unknown. That will give us 6,589.8x. Now, what we can do is we can now isolate and get x by itself. So we can see that the relationship between our number and x here is a multiply. So by simplifying it, it turns into a divide, which is what we see here. So we rearrange this to get x by itself. So we do 445575 divided by 6,589.8, and we get 68 degrees Celsius. So what that means is if we got 75 grams of ice at 0 degrees and placed it into a beaker of water, 1,500 grams of water at 75 degrees Celsius, the overall temperature when the ice has melted and has formed an equilibrium will be 68 degrees Celsius. Okay, let us now move on to question 54. So again, pause this video, have a go yourself, and then press play and we'll work through it together. So the question says, how many joules of energy would be liberated or released by condensing 50 mole of steam at 100 degrees Celsius and allowing the liquid to cool to 30 degrees Celsius? So the question is asking how much energy would be released. They're just trying to use different fancy words. So the first part of this question is we need to realize the amount of heat lost by the cooling of 100 degrees to 30 degrees. And we also need to take into account the heat of vaporization. So we'll do that next. So the first thing we do is Q is equal to mc delta T. So we want the amount of energy released. So we'll keep that as Q. So the mass, we don't have the mass, but we do have the moles. So what we can do is we can go moles is equal to mass over molar mass. So we can then go the moles, which we know it's 50 moles, is equal to the mass, which we don't know, divided by the molar mass. So we rearrange this, we move this over here. So we're going to have 50 times 18, and that's going to give us 900 grams. Now, this is what I was talking about in my previous video, and that is you need to have an understanding of these formulas, because what at first looked quite disjointed, we could see the connection that moles mass, molar mass, and that mass is what we needed to use our specific heat formula. So the mass we know is 900 grams multiplied by the specific heat of water, which is 4.184. And we're going to times it by the change in temperature. So that is 100 degrees minus 30 degrees. So 100 minus 30 degrees, that gives us 70 degrees. So there's a 70-degree jump. And we just simply multiply all of these together. And that will give us a total heat released of negative 263,592 joules. Now, we've found our heat of how much energy or heat would be released by dropping the temperature from 100 degrees to 30 degrees. So now what we need to do is we need to figure out how much energy is being lost from the heat of vaporization. So remembering that the heat of vaporization is 2,259 joules per gram. So we know that we have 900 grams of water. So we have 900 grams multiplied by 2,259 joules per gram, which means the overall heat released by condensing the steam back to a liquid stage. So that's going to give us a total heat value of 2,033,100 joules. Now what we do is we add these two values together. So if we have 2,033,100 joules plus 263,592 joules, this will give us a total value of 2,296,692 joules, which could also be written as 2.3 times 10 to the 6 joules. Okay, let us now move on to the next question. That is page 343, question 4. So the question says, calculate the mass percent of the following solutions. So let's move on now to page 343, question 4. So the question says, state the mass percent of the following solutions. So remembering that the mass percent is the mass of the solute over the mass of the solution times 100. So we have 25 grams of sodium nitrate, so 25 grams divided by, so we have 125 grams of water. So remembering that solute plus solvent equals solution. So our total solution will be 25 grams plus 125 grams. So it's going to be 25 divided by 150 grams, because that's the weight of the total solution, multiplied by 100. So if we pop that into our calculator, we get 16.7%. So that means out of the total solution, 16.7% of it is this sodium nitrate. So let us look into at the next question. So we have 0.75 moles of potassium chromate in 225 grams of water. So this follows the same logic as we looked at up here. So we have a look, we have the mass of our solvent, which is 225 grams. We don't have the moles of our solute, but we do have the moles. So our first step, moles is equal to mass over molar mass. So we have 0.75 moles is equal to the mass, which we don't know, divided by the molar mass. And the total molar mass is 194.3 grams per mole. So we rearrange this formula over here. So it's going to be 194.3 times 0.75, which means that the total mass will equal to 145.65 grams of potassium chromate. So now that we've done this first step and we now know the total mass of the solute, we can now calculate our mass percent. So the mass is equal to the mass of the solute, which is 145.65 grams, divided by the mass of the solution. So 145.65 plus 225 will give us 370.65 grams. So we divide this by 370.65 grams multiplied by 100, giving us a mass percent of 39.3%. Okay, let us now move on to page 343, question 8. So the question states, in a 75 grams of a 12% by mass solution of barium chloride, how many grams of the solute are present? Okay, so it means that we have 12% of the mass is the solute. Okay, that's what this is referring to by 12% by mass, meaning that the other 88% by mass is the solvent. So what we do here, how many grams of solute are present? We go 75 grams, which is the total mass of the solution, and we multiply this by 0.12, and that will give us 9 grams of solute. How many grams of solvent are present? We do the exact same thing. So we go 75 grams, because again, that's the total mass of the solution, multiplied by 0.88, and that will give us 66 grams of solvent. And this makes sense too, because if you get 66 plus 9, that will give us 75 grams total. Okay, so the next one, question 18. Calculate the grams of solute in each of the following solutions. So 1.2 liters of 18 molar sulfuric acid. So the first thing I'm going to do here, I can see we have molarity and we have a unit volume. So molarity is equal to moles over volume. So we have 18 molar is equal to an unknown amount of moles over 1.2 liters, meaning that the total number of moles is going to be 21.6. Now that we know the amount of moles, we can now convert this into mass or grams. So we go over here, moles is equal to mass over molar mass. So the number of moles, which is 21.6, is equal to the mass, which we don't know, over the molar mass, 98.19 grams per mole. So again, we rearrange this up here. So 28.19 times 21.6, and that's going to give us a total mass of 2,119 grams. So let us look at the next one now. This one can be a little bit more tricky because it catches people out who aren't paying attention. So the first thing I do here is we do the same plan as before. We have a unit of molar, we have our unit volume, So let's convert it into moles so we can convert it again into mass. So molarity is equal to moles over volume. So the molarity, which is 0.025, is equal to the number of moles, which we don't know, over volume, which is 0.125 liters. Please remember liters, okay? Never ever use mils in molarity. That is the easiest way to lose a lot of marks, okay? Molarity is always moles per unit liter. So by rearranging this formula, we're going to have 0.025 multiplied by 0.125, which is going to give us a total 3 times 10 to the minus 3. Now we can use this moles to calculate the mass. So we go moles is equal to mass over molar mass. So the number of moles, which is 3 times 10 to the minus 3, is equal to the mass, which of course we don't know, over the molar mass. So we have 2 lots of iron, 3 lots of sulfur, and 12 lots of oxygen. So we rearrange this formula, we bring this up here. So we've got 398.88 times 3 times 10 to the minus 3. And that will give us 1.2 grams.